Then by contractiveness of t, we have, because they are not equal, so we can take psi of tx bar, okay, psi of tx bar is equal to d of tx, okay, comma d square t of x, because psi of x is equal to x t of x. So if it is x here, then x is here, and the second argument is t of x. So if it is t x, then here is tx and here is t square x. So here we will get t square x. And now because this t is contractive, so this term is less than d of x bar, comma t x bar, this x bar. Okay, but this is what? This is by the definition of psi of r is equal to psi x bar. So it means that t of psi x bar is strictly less than psi of x bar. It means that psi x bar is the minimizer of the function psi. Okay, it means, but psi is the minimizer, which we have proved. So it means that it is a contradicting. So this contradicts that x bar is a minimizer of psi. Hence, x is a fixed point of t. So that is to say, we have assumed that t is not a fixed point. It is not correct. X is a fixed point. X bar is a fixed point of t. Now, the uniqueness, we have to prove that t has a unique fixed point of x bar. We have proved that the existence of x bar, which is a fixed point of t, and the uniqueness can be proved in the same way as we have proved in the proof of Banach contraction theorem. Second part is that for any x, we have to prove that this limit is equal to x bar. So let us start. Let us take any arbitrary x element in capital X, and if x and x is not equal to x bar, okay, if it is equal to x bar, then of course the limit of this is equal to x bar. So nothing is to prove. So if it is not equal to x bar, then what will happen? Then we can take d of t x plus x n plus 1 x, comma x bar. Okay, but x bar is what? X bar is equal, it is a fixed point of t. So it is equal to t x bar. So here is, we can write t x bar. Now we can, because t is contractive, so here is, we can take t. So you can take this is d t and x and x bar. So t and x bar for all n natural numbers. Now you see, it means what? It means that d t n plus 1 x bar is a strictly decreasing sequence of non-negative real numbers, and so converges to its infimum. Suppose that alpha is the infimum of this. Okay, and now since t and x is a sequence of points of a compact metric space. So this is because t is a map from x to itself, and x is compact. So this is a sequence of points of a compact metric space. So in the compact metric space, every sequence has a convergent subsequence. So this sequence would have a convergence. So there exists a subsequence t and kx which converges to some point, say y. Okay. Now since t and x is decreasing, we can have d y x bar is equal to this one, because this sequence subsequent t and kx converges to y, so we can write in this way. Okay, now this is same as to say that, so here we can add one more, the sequence and subsequence will converge to same point, and this is what? This is we are assuming that it is equal to alpha, so this is equal to alpha. So now if alpha is not equal to 0, then what will happen? If alpha is not equal to 0, it means that y should not be equal to x bar. So then y should not be equal to n bar. And so we have alpha is equal to, because from here alpha is equal to dy x bar. Okay. And of course y is not equal to x bar. So this is greater than, strictly greater than d ty t x bar by the contractiveness of t. But again, t x bar is equal to x bar, because x bar is a fixed point of t. So instead of this, we can write x bar. Okay. Now y is equal to, so this is equal to, we can take because y is the limit of this subsequence. So instead of this, instead of y, we can write, we can take the limit k approaches to infinity, t and k x, and x bar is here. Okay, and now this we can combine, then we can write in this way. And now of course the sequence this converges to alpha. So this is equal to alpha. It means that alpha is strictly greater than alpha. This is the contradiction. Okay, so what we assume that alpha is not equal to 0, it is not correct. So alpha must be equal to 0. So alpha is equal to 0, so this term is equal to 0. It means that if this is equal to 0, it means that t and x limit t and x as n tends to infinity converges to x bar. So that is the proof of the result when the metric space X is compact and T is contractive, not necessarily contraction. Now we have a very simple result which provides the criteria by which we can see that whether a differentiable, continuous differentiable function, continuous differentiable function on defined on a compact on a closed interval to itself, whether such kind of functions have a fixed point or not. So we have the criteria. So the following result is useful to test whether a differentiable function is contraction or not. So how? So let us take x is equal to AB, closed interval AB. Now keep in mind, closed interval, closed and bounded interval are compact. And of course, every compact metric space is complete because it is sequentially complete, so it is complete. So here is this is a compact, this is closed and bounded interval. So this is a metric with the usual metric, and T is a map from closed interval AB to itself, and this T is a continuous function which is differentiable on the open interval in the interior of this one, open interval AB. Then T is a contraction mapping on X. T is a contraction mapping on X if and only if there exists a real number alpha which is strictly less than 1. Keep in mind, alpha is strictly less than 1, not equal to 1, but of course it is greater than 0. So alpha lies in the, it must be greater than 0 and strictly less than 1, such that the mod of the derivative t dash x is less than alpha, less than or equal to alpha for all x lies in the open interval AB. So this is the criteria by which we can see that whether a differentiable continuous function defined on a closed interval to itself is contraction or not. So let us prove first this theorem. So suppose that T is a contraction mapping. T is a contraction mapping, then by the definition there exists alpha lies in the open interval 0, 1 such that mod of Tx minus Ty is less than or equal to alpha times mod of x minus y for all xy in the closed interval AB. Here is mod we are taking because we are considering the x, the x is equal to closed interval AB with the usual metric. So usual metric is what? Usual metric is dxy is equal to mod of x minus y. So we are using the usual metric, and that's why we are writing the mod here and mod is here. Now then for any x and x plus delta x is the increment in x. So in the closed interval AB we have, so what we can do here is t of x plus delta x minus t of x. So this is equal to from here, so because this is true for all xy, so instead of x we can write x plus delta x, instead of y we can write x. So this is less than or equal to alpha times mod of x plus lambda x minus x. X is cancelled out, so it is equal to alpha times mod of alpha times delta of x. Now For delta is not equal to 0, so we can take delta on the other side and take the mod, then this term is the mod of this term is less than alpha. And now we can take the limit both the side as delta x approaches to 0. So delta x approaches to 0, we have this term, and this is what? This is nothing but it is the mod of t dash x, derivative of t at x, okay, but this is less than epsilon, so we get the mod of t dash x is less than epsilon. Now let us prove the converse part. So converse, assume that there exists a real number alpha which is strictly less than 1 such that mod of t dash x is less than or equal to alpha for all x in the open interval AB. Then by mean value theorem, for any x which is not equal to y in the closed interval AB, there exists an element C in between A and B such that t dash C is equal to t of x minus t of y divided by x minus y. And now we can take the mod both the side. So we take the mod both the side, but this is equal to, by our choice here, by our assumption, this is less than or equal to alpha. Okay, now you can take mod of x y on the other side. So hence t of x minus t of y, mod of this is less than or equal to alpha times x minus y. This means what? This means that t is a contraction on AB. So this way we can check whether a function defined on a closed interval AB, okay, which is differentiable and continuous, so whether this function is a contraction or not. Now here is I present several exercises. Some of them are given with the solution and some of them are not. Now look, here is the first exercise. I consider x is equal to the closed interval 1 infinity, okay, with the usual metric space, and t map from x to itself, which is defined at tx is equal to 10 upon 11 x plus 1 upon x, okay. Then the question is, prove that t is a contraction mapping. So prove that t is a contraction mapping which Lipschitz constant alpha is equal to 10 upon 11. Okay, now this you can see that this here you can you have this function. This is your interval. This is, keep in mind, this is your this is your metric space with the usual metric. But keep in mind, here is we have to prove that t is a contraction map. The question is whether we can apply the previous theorem here or not. Number one. Number two is that what will happen if we take without 10 upon 11, if tx is equal to x plus 1 upon x, even then t is a contraction map. Okay, so try to this one and I will give you the answer. Similarly, if we have x is equal to r is the usual metric space and t is a map, tx is equal to x upon a plus b, where a and b are real numbers, then prove that t is a contraction if a is greater than 0. Now look here. So this you can prove very easily. Just you take mod of t of x, okay, mod of t of x minus t of y is equal to mod of x upon a plus b minus y upon a minus b. So this is cancel out and you will see that if a is greater than 0, then t is a contraction. So it is very simple, not very difficult task. Now for the third exercise, if we consider the closed interval 0, 1 and the map t is defined as 1 over 7 x cube plus x square plus 1. Okay, then prove that t is a contraction with Lipschitz constant alpha is equal to 5 upon 7. So there are two ways to prove this theorem. Okay, number one, you use either this theorem, previous theorem which we have proved, this theorem, because the t is a this t is a closed interval, so and t is continuous differentiable. So here is t is a continuous and differentiable. This is continuous differentiable defined on the closed interval AB. Okay. and then you will have to prove that the derivative of this, okay, the derivative of the mod of the derivative of this is less than or equal to alpha, and alpha is equal to 5 upon 7. So this you can prove very easily, or you can do in this way. You can use the definition of the contraction, that is to say mod of t of x minus t of y. Okay, so then you can use the mod of x cube minus y cube is equal to mod of x minus y into x square plus xy plus y square. So you can use this identity, or you can use the previous theorem. Then you can prove that this map T is a contraction mapping. Similarly, suppose if you have x is equal to set of all rational numbers greater than or equal to 1 with the usual metric space, and T is a mapping defined as Tx is equal to x upon 2 plus 1 upon x. Then T is a contraction map, okay, with Lipschitz constant 1 over 2. So this you have to prove. We have another exercise which says that if x is equal to r and t is a mapping defined as Tx is equal to cos x, then T is not a contraction, but it is contractive. Okay, why it is not contraction? Now keep in mind, as I have mentioned here is, if there is 10 upon 11 or 9 upon 10 or 5 upon 11, 5 upon 7, any number which is sticky less than 1, we are multiplying. So then we can get this one. Same as here, you see here is, if we are taking Tx is equal to cos x, okay, then it is not contraction. But if we multiply this term by, say for example, 99 upon 100, then it is a contraction. Okay, how we can prove? We can use this identity mod of sin x, cos x minus cos y. So this we use the identity cos x minus is equal to 2 times sin x minus y divided by 2 into sin x plus y divided by 2. So this you can write as the mod of the first term into the mod of the second term. Okay, but you see here is this mod of this. Okay, this is always less than, because the sign value, mod of the sign value is always less than or equal to 1. So this is less than or equal to 1. So we are multiplying this term by a term which is less than or equal to 1. So the whole term is less than or equal to this term. Okay, but because we know that sin mod of sin w is less than w for all w is not equal to 0. So for x is not equal to y, you can see that this is strictly less than 2 times mod of x minus y divided by 2. But this is what? This is equal to mod of x minus y. So here we have proved the mod of cos of this is strictly less than mod of x minus y. It means what? It means that the map T defined by this is a contractive map. Okay. Now you have to prove that it is a contraction. Not only this is not this one, but this one. So you multiply it by this one. What you will get? You will get here is everywhere. So you take 99 upon 100. So you got 99 upon 100 or 1 upon 10 you can take, or 9 upon 10 you can take. So here you will take 9 upon 10, 9 upon 10, 9 upon 10 or 99 upon 100. So you will get 99 upon 100. So it means that this is less than 99 upon 100. So 99 upon 100 would be the contraction mapping. So this is less than or equal to this one. Otherwise this is sticky less than 1. So this map is a contraction map, but this map is not. This map is contractive and this map is contraction. Similarly, you can prove that the map sin x is a contractive map, but it is not a contraction. Again, to make this map contraction, you will have to multiply by some terms here which is strictly less than 1. Okay. Now, the next exercise is where we consider x is equal to the closed interval 1 infinity. Okay, with the usual metric space, and T is defined as x square plus 1 over x for all x in x. Now, prove that this map has no fixed point. Okay. How can we prove it that this has no fixed point? It is not like this. We are not finding any x, okay, such that Tx is equal to x. We will have to prove. So you have to prove, because this metric space with the usual metric is a complete metric space. But you will have to prove that this T map is not a contraction map. So because this is complete, this is not contraction, so you will not have any fixed point. Okay. The second thing is, let us take x is equal to r cube. Okay, is a metric space with the usual metric, and T is defined as Tx is equal to 1 over 2 cos x2 plus 1, comma 2 over 3 sin x3, comma 3y4 x1. Okay, then show that T is a contraction map, and deduce that the system of equations this has a unique solution. So this you can get very easily. If suppose this has a unique fixed point, so the fixed point would be equal to x1, x2, x3. So x1 is equal to this, x2 is equal to this, and x3 is equal to this. This is what? This is the same as this one. So it means that it is a unique fixed point. Now here is very interesting exercise, and you must try it, as I am mentioning from the very beginning. Whenever you have any, you have to construct any example, okay, or you must try to consider the discrete metric space. So here is the question that proves that every contraction mapping, okay, every contraction mapping defined on a discrete metric space X is a constant mapping. So this can be proved very easily. It's not a difficult task. Now let's take x is equal to r2, and t is defined by this way, that txy is equal to y upon 10, comma x upon 20. Then show that t is a contraction on x. Now I go to the next exercise. We say that if x is equal to 1 infinity is a metric space with the usual matrix, and T is defined as Tx is equal to x upon 2 plus 1 upon 2. Okay, this you can see this, the proof of this one from here. So x upon 2 plus 1 upon x. Then show that T is a contraction, and conclude that it has a unique fixed point, and also find the fixed point of T. So first let us prove that T is a contraction. Okay. Of course, this is a complete metric space, so T is a contraction, so it would have a unique fixed point. So first we need to show that T is a map, because you keep in mind T is a map from X to R, and X is what? X is 1 infinity. So first we have to prove that T is a self map. Keep in mind, whenever we are defining the fixed point of a map, then the map is a self map, then from T from X to X. But here is T is a map from X to R, where X is a subset of R. Okay. So to prove that it is a contraction map, first we will have to prove that the T of capital X must be subset of X. That is to say, T of X must be equal to X, or subset of X. So this we will have to prove that it can be shown by proving that the minimum of T over X is 1. Okay, because it will not take any value which is less than or equal to 1. Then we can say that T of X is a subset of X. So we first find the minimum of T over X. Now since T is differentiable, okay, T is differentiable over the open interval, this one, okay, and increasing as x tends to infinity. The minimum is attained either x is equal to 1, or at the point where the derivative of the function is equal to 0. Okay, so Now you can take the derivative of the function is equal to 1 over 2 minus 1 upon x square. And so that the derivative, if the derivative is equal to 0, then what we will get? We get x is equal to under root 2. Okay, but if we take t of under root 2 is equal to 2 upon under root 2, which is greater than 1. Okay, and also t of 1 is equal to 3 upon 2, which is greater than 1. So in all these values, the minimum values, the value of t at under root 2 at under root 1 is greater than 1. It means that the t of x, so in any case t of x is greater than 1 for all point x in this set x, and therefore tx is the subset of x. Now the second part is we will have to prove that t is a contraction map. So t is a contraction map. So C is continuous and differentiable on the open interval 1 in infinity. We can calculate the derivative t dash x, which is equal to mod of 1 over 2 minus 1 over x square. But this is less than or equal to 1 upon 2. And this, of course, 1 upon 2 is less than 1. Okay, keep in mind, we are considering that x is in the open interval 1 infinity. So it is greater than 1. So it is less than 1. So this is, the whole thing is less than or equal to half. So this is less than or equal to half, and half is less than 1. And therefore you can see that t is a contraction map by theorem 6.1.4. And since x is complete by Banach contraction theorem, it has a unique fixed point. Okay, and it would satisfy this inequality because t of x is equal to x upon 2 plus 1 upon x, it must be equal to x. So just solve this one. If we solve this one, what we will get? We get x square is equal to 2, and therefore x is equal to under root 2 is a unique fixed point of t. So this way we can prove that t has a unique fixed point. Now there are 3 exercises. Almost all the exercises are 1, 2, 3. They are almost similar exercises where we consider x is equal to the bounded B01 space of all bounded real valued functions defined on AB with submatrix. Okay, and T1, T2 are defined in this way. T1 is defined in this way, T2 is defined this way. Then show that T1 and T2 are contraction and find their unique fixed point. The second one is we are considering the x is equal to C01, set of all continuous real valued function defined on the closed interval with the submetric. Okay, keep in mind here we are taking submetric, so here is also submetric and t is defined in this way. Then show that t is a contraction map. Okay, the third one is we are considering x again C01 and t is defined in this way. Okay, then t is a contraction. Now look, here is the proof of the last one, because if we will prove the last one, so these 3 exercises are almost same. So I will give you the proof of the third one and you can prove the first 2 by yourself. So here is clearly a fixed point of t is a solution of the integral equation, this one. Okay, then by the definition of submetric we have d t u t v is equal to supremum of this one. Okay, but this is less than or equal to, you can take because you can take the integral from 0 to infinity. So you have ut minus vt, because this is ut minus vt. Okay, so this is less than or equal to this. So you can take and therefore this is what? This is equal to duv, because this is duv is with the submetric. So this is equal to sub. So this is less than or equal to half duv. But if you take alpha is equal to half, then t is a contraction map. Okay, and we have already seen that C01 with respect to submetric is a complete metric space. So by Hahn-Banach theorem, it has a unique fixed point. Now the question is how we will calculate. How we will calculate the fixed point of t. So to find the fixed point of t, we use the iteration process as developed in the proof of Banach contraction theorem. How we will develop? We can start with some initial gas. So let us take our initial gas is U naught. Okay, U naught x is equal to 0 for all x. Okay, then repeatedly apply t to get a sequence un of the functions. How we can take? You apply u1, we can write you apply t over here, so you will get t of u naught x. Okay, but t our and t u naught, keep in mind our function is t u x is from 0 to infinity ut minus 1 upon 2 dt. Okay, but u naught is equal to 0, so what we will have only minus 1 upon 2 dt. So this is minus 1 upon 2 dt. Integrated, you will get x upon 2. Now this is your u1x. Okay, and now operate t. So you operate t on u1x and denote this by u2. Okay, so denote it by u2. Then you apply here is again and put the value over here in the function, you will get this one. Again apply t over here, you will get this one. Continue in this way. If you continue in this way, and an easy induction argument shows that the nth term of this sequence is would be like this. The nth term would be like this. And now, so the sum is equal to, if you take the sum of this is equal to, so this is equal to, the sum of this is equal to 1 minus exponential x upon 2. Okay, so this way you can calculate the value of u, which is the function is this one. So this is the way to calculate the value of to calculate the fixed point of the mapping T. Now, suppose we are considering x is equal to C0A. Okay, A is any number, and this is a space of continuous function defined on 0A with submetric, and H is a function, and T is a mapping which is defined as TUX 0 to x ut dt plus hx. Okay, then show that T is a contraction map if and only if alpha is less, A is less than 1. So here is A is less than 1 if and only if. So the same way as we have proved the previous exercise, you can prove this one. And if H is differentiable, then write down a differentiable equation with initial condition, or for which the fixed point of T is the unique solution of C0A. Okay, now a very interesting exercise I left for you, and if you can do this exercise, it means that you have understand the Banach contraction theorem. So in other words, you can say that if you see that this exercise is nothing but it can be treated as the converse of the Banach contraction theorem. What is the converse of the Banach contraction theorem? We say that if Tx is a complete metric space and T is a self map from x to itself such that dTxty is greater than or equal to alpha times dxy. Okay? In the Banach contraction mapping is what? It is less than or equal to. Here is it is greater than or equal to for some alpha is greater than 1. For some alpha is greater than, but in the Banach contraction mapping, alpha must be less than 1. Okay? So here is we have almost reverse of the contraction, and assume that Tx is equal to x. Okay, then prove that if the condition this is hold good and Tx is equal to x, then prove that first you prove that T is a one-to-one mapping, and not only this, prove that T has a unique fixed point x bar, which is nothing but it is equal to T raised to the power minus n x is equal to x bar for some x in x. Okay, so this is very interesting. and you can try to yourself. Okay. So now I close this talk over here, and in the next talk we will see that some other applications of Banach contraction theorem. Okay, welcome you all again in this talk, and here we will discuss some applications of Banach contraction theorem and some other theorems which we have proved or which we have discussed in the last few lectures. Okay, so first we will consider a very simple application to the system of linear equation. So let us take here we have a system of linear equations, system of n linear equations with n unknowns. Okay, and then this system can be written in this form. Why? How you can take x1. So you take x1, rest of the term you take on the right hand side, and then you divide. Here you can take x1. So you take x1 is equal to, here is, we can write this first one as x1 is equal to this one. Okay, so I write x1 is equal to x1, and rest of the things you take on the other side. Similarly, x2 you can write in this way, x3 and x4 you can write in this way. And now let us take alpha ij is equal to aij. This is equal to aij plus canonical delta ij, where canonical delta ij, the value of canonical delta is equal to 1 if I is equal to j and it is equal to 0 for I is not equal to 0. Okay, then this system is equivalently written as, instead of this, xi is equal to summation j runs from 1 to n alpha ij xj plus bi for all I runs from 1 to n. And if x is equal to x1, x2, xn, and a we are treating as a matrix, a11, a12 and so on, this matrix, and b is equal to, the matrix is b1, b2, bn, then the previous system, okay, for this system can be written as x is equal to ax plus b. So if we define a transformation t from Rn to Rn by that tx is equal to ax plus b, then if t is a contraction map, then what will happen? If t is a contraction map, then tx is equal to x. It means that x is equal to ax plus b. It means that this holds good. So if t has a fixed point, then this would have a solution, or t has a unique fixed point, then this would have a unique solution. It means that the system of n linear equation would have a unique solution. So everything is depending to prove that whether the map transformation this map is a contraction map or not. And this map T is contraction or not, it depends on the choice of the metric defined on Rn. So as we have seen, there are several kind of matrices which we have defined on Rn. So first, let us take x is equal to Rn be a metric space with the metric d infinity xy is equal to maximum of xi minus yi. So if the mod summation j runs from 1 to n mod of alpha ij is less than or equal to alpha, and alpha is strictly less than 1 for all I runs from 1 to n, then the linear transformation this, okay, which can be written in this form, and this can be written in this form, and then this can be written in this form, and this can be written in this form. So the linear transformation of n linear in n component has a unique solution. In other words, you will have to prove that this transformation has a unique fixed point. So this you can use, keep in mind we are taking this assumption, okay, and this is our metric. So with this one, since x is equal to Rn with respect to the metric d infinity is complete, we have already proved, and it is sufficient to show that t, the map T defined by this is a contraction. So let us take d infinity tx ty is equal to this one by the definition, and this is less than or equal to, so here you can take a summation mod of alpha ij into mod of this one. But here we can take a summation maximum of I runs from 1 to n and j. So you can take a j and this you can take a, so here we are taking the maximum over this one. So here taking and you can take this on the other side. Okay, but this is what? This is nothing but it is our dxy. So this is our dxy and this you will get only here is equal to. But this is, we have proved that the maximum of this is less than alpha. So this is less than alpha, and so this is less than or equal to alpha, where alpha is less than 1 and therefore T is a contraction map. And so by Banach contraction theorem, the system of linear equations has a unique solution. Now the other, we have the exercise, or you can say if x is equal to Rn, we have metric space with the metric d1 xy is equal to summation I runs 1 to n mod of xi minus yi. And if this condition holds good, that is, this is less than 1, then the linear system of equations in n unknowns has a unique solution. Again, you will have to prove that the T defined as Tx is equal to Ax plus B is a contraction. So this you can prove in the same way as we have proved, and that's why I have left it for your exercise. So here you can see that you can write this is equal to mod of this one, and then again you can write in this way, you will get this one. Similarly, if you are considering in another metric, okay, this usual metric on Rn, then you will have to consider this condition. And again by using the same technique, okay, so here you can use this way, you can prove that dt is a contraction mapping. So again, I am not going to give the detail, it is already given here. So now we consider another application of Banach contraction theorem. Okay, another application to the differential equations. Okay, so we are considering and we will use the Banach contraction theorem to prove the existence and uniqueness of the ordinary differential equation with the initial condition. So let us consider the ordinary differential equation dy over dx is equal to fxy, and the initial condition yx naught is equal to y naught. Okay, so we will prove that this differential equation, ordinary differential equation, has a unique solution. It means that we will have to define some function, okay, and which is a contraction. So what we will do, it is called, so we have the following result, which is called Picard theorem. So Picard theorem is that let f, a function of two variables, be a continuous function of two variables defined on the rectangle A, which is as xy. X lies between A and B and y lies between C and D. A, B, C, D are any real numbers. Okay, and satisfy the following Lipschitz condition in the second argument, that is, there exists Q is greater than 0 such that this is less than or equal to Q y hat. So this means that f is Lipschitz continuous in the second argument. Okay, and let x naught y naught be an interior point of A. Then the differential equation this with the given condition this has a unique solution. That is the Picard theorem. Now to prove the Picard theorem, first of all we show that the problem of determining the solution of this is equivalent to the problem of finding the solution of the integral of an integral equation. What is that? If y is equal to gx satisfies the differential equation this and has the property that this initial condition holds good, then integrating the differential equation this both the side from x naught to x, we obtain g of x minus gx naught is equal to the integral from x naught to x f t gt with the initial condition g of x is equal to y naught plus this integral. Okay, Thus, a unique solution of the differential equation, this with the given condition is equivalent to a unique solution of this integral equation. Now, we apply the Banach contraction theorem to determine the solution of this one. So, for that, by the Lipschitz condition of f in the second argument, there exists q such that this is holds good. Now, since fxy is continuous on a compact subset A of R2, keep in mind A is a or compact subset of Rn. It is bounded, and so there exists a positive constant m such that mod of fxy is less than or equal to m for all xy in A. Now, choose a positive constant p such that pq is less than 1. And the rectangle B, okay, so B we can take x lies between x0 and and add p both the side. And here is y, so here is y0 and add both the side minus pm. Keep in mind m is the upper bound of this function. So this okay, rectangle this. So this rectangle is contained in A. Let x be the set of all continuous functions. So y is equal to g of x defined on this closed interval minus p plus x0, p plus x0 such that d gx y0 is less than or equal to mp. Then x is a closed subset of the complete metric space, this with the sup norm. And since this is complete, okay, this is complete, x is a closed subset of this, so x is complete. Okay, now we define a transformation T from x to itself. How we define? We define in the following way, that T of g is equal to h, where h is equal to y0 plus integral from x0 to x f of t g of t dt. Okay, and then we will prove that this t is nothing but it is a contraction mapping. So, since dhx y0 is equal to the supremum of this one, and supremum of this is less than or equal to m times x minus x0, and this is less than or equal to mp. Okay, it means what? It means that hx in x, and so t is well defined. Number one. Number two is for any g1 in x, we have t of g1 is equal to d h1, because the function h is defined in this way. And this is what? This is by definition is equal to this thing. But this is less than or equal to this one. And again, you can take this is equal to supremum, so we can write in this way. And this is by definition, it is less than or equal to p times d g1. So this is less than or equal to this one. That is to say this. And now whereas alpha is less than 1, because alpha is equal to qp and qp is less than 1. So hence t is a contraction mapping on x into itself, and therefore by Banach contraction theorem, t has a unique fixed point, that is g star in x. And this unique fixed point g star is the unique solution of the differential equation 6.1 with the given initial condition. So this way we have given the application of Banach contraction theorem to the ordinary differential equation with the initial condition.